Hello everyone, my name is Kenji Kimura. I'm a current clinical informatics fellow, and I recently learned about system development lifecycle, and I thought I'd share what I learned to everyone. So before I go into details about the system development lifecycle itself, I wanted to cover why it is important to have this concept. This graph is showing the cost to detect and fix bugs. The x-axis is time, the y-axis is cost. The blue is cost to detect, and the orange is cost to fix. So earlier in the phase of developing your system, cost to detect is expensive because you don't really know exactly what's wrong with your system just yet without having people use it. But if you know what's wrong with your system, it's relatively easy to fix. However, imagine that you, made a software and you're gonna go live with it. Now everybody's using it and you're getting feedback from everybody. So cost to detect is relatively low because everybody's screaming at you, hopefully not screaming, but letting you know that this is not working. Then, however, is a bit more difficult to fix at that point because your system is already implemented. You might have to pause the entire system to update it. Therefore, to have a very good system development lifecycle planned out is important, and that is what I'm going to cover right now. This is just a brief graph showing what we want to accomplish. Initially, your system is going to go through the phases of concept, development of the system, production, and then utilization. Initially, your return of investment is negative, but at some point, hopefully you break even and people are starting to use it, and then you're going to start to get return of investment here. This is what we want to accomplish, and hopefully less bugs to fix at that point. So system development lifecycle, the name is kind of intimidating, but it's actually a relatively easy concept. And I think a lot of us are actually doing it naturally. We're just trying to give it a structure and a framework and define the system development lifecycle. So let's get into it. So this is the cycle. It starts from analysis and it goes through mainly 4 phases. Different institutions might have different or more granular SDLC, but this is the big picture of what SDLC basically covers. So let's start from analysis and planning. Here, you are going to define the problem space. What do you mean by problem space? That is, what's wrong with the current system? As in, if you are using maybe paper record system and you're trying to move to electronic record system, what are the problems currently and what are the solutions? What are the benefits that you're going to get from moving into electronic record system? You want to identify the requirements that the electronic record system wants to hit. What are the cost and timeline? And you might have multiple goals, but you want to prioritize them. And then have a milestone / decision gates, which is when you have first section of the project completed. You want to move on to the second one, but there is a decision gate where you want to make sure you checked off all the points that before you move on to the second part of your project. You want to do a risk analysis and trade-off analysis. Maybe not all is good and great about an electronic record system compared to the paper system. And you have to even think about what we're going to do when we're going to retire the new system. How are you going to discard the hardware and software and data? So analysis and planning is perhaps the most important part of SDLC, and it's worth putting a lot of our time and mental energy into it. And then you're going to go into build or develop, and you're going to test the system. You're going to define and refine the system as you build it. And perhaps, especially in the hospital system, you might have a vendor that already developed this, and you might want to buy it from them or license it from them. Uh, and then once you bring it into your environment, as in maybe the hospital or clinic, you want to test it, see if it will integrate well with your current environment. Would it communicate well with other systems in the environment? And then you want to start to train the users and get feedbacks. And once you get the feedback, you can go back to analysis and planning for that specific feedback, and then build and test. And then implementation. This is where the product or the system is going to be executed in the real environment. This is the most, perhaps the expensive part. You have to purchase the software, you have to purchase the hardware, and install it in all the machines, and then test and train the users, and inspect and verify and get feedbacks. Generally, you want to move from analysis to planning, build and test and then implement. But of course, as you get more feedback from the users, you might want to go back to analysis and planning for that specific feedback, and then update, as in build, and then come back to implement again. So you don't have to be too rigid. It is important to know where you are as a team, that you're in an implement phase, but you don't want to be too rigid that you can't go back to plan and analyze. But there's some flexibility that you always have to have as you lead the team. And then finally, maintenance and support. The system is operating in its intended environment. Disaster recovery is in place, and security and safety is in place. And you're still getting feedback. And as you get feedback, you're going to close the loop and back to analysis and planning, development and testing, and then implement, and then maintain. So the first cycle is going to be the most hardest part. But as you go through the cycle, it should get easier and easier, smoother and smoother as you update the system and people are starting to understand how the system works. Now, retirement is a little off from the general cycle, but it is there when you want to make a big update, replacing the system with another new system. And things to consider then is that you might have two live system going parallel, because you're in a transition state. You can't just switch off one and then switch on the other. You might want to gradually merge and then eventually switch off the old. You want to make it more seamless. You have to also think about how the data is transferred to the new system, and think about also the hazard risk that might come with it, as in when you are discarding the old hardware or software, and how are the data secured, and also the cost that comes with discarding the hardware or software. So in summary, defining a system development lifecycle establishes a framework to ensure that the system meets its required functionality throughout its lifecycle. And again, SDLC, there's many kinds of SDLCs, but this is the main big framework, these four big components and retirement. And it can be sequential, as in it could be one way, or iterative. And I think in most big projects, it's iterative, as in these arrows could be bidirectional, although there is a general flow of one way. And then the benefit of SDLC, it allows us to understand and evaluate the system better. It allows us to control and learn about the system better. I think this is the most important, the communication part with the team. We know exactly where we are in the phases of the development of the system. And it allows us to know where to improve, predict what it will do, and also put milestones and get approval for developing further your system. So these are a lot of these benefits that comes with designing and really having a clear SDLC in place before you start moving and just jumping into the pool. So that's the big idea of SDLC. And here are just a couple of examples of where SDLC wasn't fully um, defined, and maybe and I'll present another one that was fully well defined. So here, um, it was in 1980s when Direct 25 came out. It was a huge upgrade from the older version. This had more software that was automated. However, uh, the old system actually had a lot of checkpoints for the technicians to have to go in and then reorient the patient, and there was a lot of more manual work. But on the other hand, that also came with checkpoints. So it made the technicians or whoever is operating to make sure that one component is thoroughly done versus they move on to the next part of the procedure. However, here with Therac 25, it was like almost one push and then the system just did magic for you. It was very efficient and uh, less hands-on work for the operator. However, um, the downside that they didn't think about when they were developing is that there wasn't a checkpoint for uh, the procedures. So once you hit go, and if you don't notice that you programmed it wrong, then maybe the patient could get overdose, and that's what exactly happened. And in addition, they didn't really document the software well, that they couldn't trace where they really failed upon developing this system. So documentation is another important part when you are developing a system lifecycle. And then ending on a better news or better fact is NeoNurture. After World War II, a lot of incubators were actually engineered for babies, preemies, so that they could grow into grow fully. And in developed countries, it was still expensive, but it was getting popular. However, it's very expensive, and two, these parts to build this were very sensitive. It easily broke, and you had to repair them. So in developing countries, it was very difficult to bring this in and help the babies. So doctors and engineers came together, and they said, how can we build this? And one big key component was, how do we maintain the incubator when it's broken? So the doctors and engineers looked around the environment there in the local country, and they noticed that there was a lot of Toyota trucks running, and everybody knew how to fix Toyota cars' headlight. So they said that how about if we warm up the baby with the headlight of the cars? And actually, they were able to make an incubator that was just as good as the high quality one. Um, and the great thing about this one was that they planned it well, analyzed it well, they made it to implementation, and then they even uh, thought about how to maintain it, as in when the parts broke, the local people were able to immediately bring in more parts and fix it with their own hands rather than having to get a very expensive part from somewhere abroad. So they really designed the system very well, and they were able to implement it, and they closed the system, as in maintain and then analysis and planning. They were able to maintain the system throughout because it was able to maintain very relatively easy. And this is just a reference that I use for this presentation. And thank you very much for listening to my presentation. I hope it was useful, and uh, it gave you a big idea, the concept of SDLC. And please let me know if there's any comments that you have, and if there's some other topics that you want me to cover in biomedical engineering and informatics. I'd be happy to do that, and I would love to learn from you as well. Okay, so thank you very much for listening.